Howdy, my name is Jedediah.
Howdy, my name is Kevin Shi.
Today we are presenting our research for CSCE439 on how graph learning can be used for computer hardware security applications. We often consider vulnerabilities in software in our technology use, spending time, money, and effort on making your computer software as secure as is convenient. But computer hardware is just as important and is increasingly attacked by malicious users. While software can be modified or updated after vulnerabilities are discovered, hardware vulnerabilities more likely than not just stay with the product as long as it's in use by the consumer. So in our work, we specifically focus on hardware trojans and intellectual property theft as sources of destruction and damage caused through hardware design.
So in order to analyze our data, we need to first understand the design automation context. The hardware specification is first developed at the register transfer level, RTL, which is then compiled and turned into logic gates, appropriately named gate level netlist, GLN. This stage is then developed into a virtual layout and then a physical IC, which can no longer be altered. So we're specifically going to look at the RTL and GLN design stages, which are still digital implementations.
So there are already several solutions presented in analyzing and tackling design fraud and hardware trojans, but often they're impractical and also slow. So traditional methods include analytical solutions and heuristic solutions, but they're mostly specialized to specific ICs. Machine learning applications have also been proposed, like such as using SVMs. But most of the time, they involve using non-Euclidean structures, and hardware design files in nature are non-Euclidean. So this makes it very difficult and also very slow in terms of pipelining data in a convenient way.
So the issue with hardware design languages, netlists, and layouts, as mentioned earlier, is that it requires an expertise for the analysis of such data. But with graphs, you can convert the non-Euclidean data into Euclidean vector spaces, which can then be used as inputs to traditional machine learning models as normal.
So here's a layout of our plan and what we envision as a solution for this. So we start at the beginning with HDL or RTL files, including at the gate level netlist as well. And we convert this into a graph representation. This graph representation is not just a simple graph representation as we normally think of, but rather a graph embedding, which gives a lot more information and is much more easy to input into neural network pipelines. So here we can also see that we envision it being used in different neural network applications for detecting Trojans, as discussed earlier, and also for piracy detection as well.
So our research methods are based on HW2VEX implementation, as well as some conceptual understandings from a couple other resources. Here we're going to demonstrate HW2VEX implementation and then demonstrate our own implementation and our results.
All right, so here we're going to look at a inspiration from HW2VEC, which is the paper that originally proposes this solution. This draws heavily from their repository shown in their paper. So after we get our original code set up, we're going to move on to what they describe as use case 1 in their paper, which is the creation of the graph embedding. The creation of the graph embedding involves, pre-processing graphs, generation of graphs, and eventually going on to actually process it using different lexical processes for creating a more powerful representation that can be used in the graph convolutional networks used in their architecture. So here we're going to move on to use case 2. And in use case 2 in their paper, they discuss actually using it for hardware Trojans. So we're going to pre-process the graphs and generate graphs and then use it for creating our pipeline as shown here, given the selected arguments. And we're going to go down a little bit more and see our configuration for the model. And here we can see the actual stages created here for our graph convolutional network, being the graph pooling, the graph readout, and also the graph convolutional stage. And after this, we're going to move on to training as it's pipelined incorrectly, and then we're going to see our actual training information and our results. So we actually get a very high F1 score and we get a perfect accuracy. Both are perfect, showing that this is an excellent recreation of what we see in the paper. So from here, we're going to move on to what they describe as use case 3, which is the IP piracy detection. And it's very similar to what we see before. So we're going to move on and go into our results. And also, we're going to discuss the results here a little bit. So it wasn't quite as accurate as we see in the paper, the F1 score and the accuracy kind of level out at around 70%. But I think the main point of seeing all of this is how easily we can access using their code and how easily using graph learning can be for using non-Euclidean structures in machine learning. And I think that's a huge part of our inspiration for this problem.
So similar to HW2X implementation, we also go over 3 use cases, but we dive a little deeper into the preliminary steps. So here we have all the helper functions, and then here we get to basically our plan. So before we can even generate our graph embeddings, we actually need to first, for every RTL/GLN file, determine if we want to use an abstract syntax tree or a data flow graph. And so when we try to generate our abstract syntax trees for the Trojan infected and Trojan free case, we run into 2 problems. One, that it's computationally intensive, and it's very difficult to actually identify the features that classify it as Trojan free or Trojan injected. So even with the filters um, that we apply to the graph and then the max step of 5, we still get the same problem. And so we move on to the data flow graph for the same cases, and we definitely identify features that are a lot more distinct for the infected and the Trojan-free case. And so we decide to use a data flow graph for each of the files. Whenever we're um, generating our graph embeddings, we basically generate a data flow graph for each one of the files that we're looking at. And then using the helper functions, we look at all the graph features for those data graphs, and then we apply that to our embedding. So we have a train embedding and then a test embedding that we use for our machine learning models. So we have all the warnings for all the files that we're looking at. And so here we're actually visualizing the graph embeddings, except you might notice that a graph embedding has more than 3 dimensions. So here we're using a method called principal component analysis, where we reduce the dimensionality by basically assigning weights to each one of the graph features, and then using those weights to create our principal component 1, 2, and 3. That way we can actually visualize our graph in a 3-dimensional space and kind of be able to tell more easily what is going on. And so we actually apply our machine learning models, our random forest classifier, case nearest neighbor, naive Bayes classifier, and then our multi-layer perceptron classifier, our neural network. And then we get this result. So we have our confusion matrix for our random forest classifier. It's pretty good, and then not as well for the case nearest neighbor. We have basically a perfect result for the naive Bayes classifier, and then for the um, our MLP classifier, it doesn't do too high. So here we have accuracy scores. And then we get into our use case 3 equivalent, and that's our IP piracy detection. And so the structure is overall the same, and then we actually illustrate the embeddings here as well, where we can see the data flow graphs as 3 dimensions. What we do different with the IP piracy detection is that we use a little more of a naive method. Basically, we have a threshold distance for each one of the clusters, and if it passes that threshold, we call it as likely piracy. Here it's illustrated for which clusters of files have too close of data flow graphs where we might identify them as potentially pirated IP.